You're trying to find the light at the end of the tunnel. We have 2 more units after this one that we'll look at. This one is the differential equations one. It is kind of a hodgepodge of topics. This is going to be a unit that does have some BC only stuff in it that's also not found in AB, but it will have a lot of AB stuff in it as well. Guaranteed, there will be one question, free response question on your AP exam that is a differential equation topic, which is a very broad topic, but guaranteed there is going to be one that's on the AP exam, so it is kind of weighted as a heavy topic in terms of like what you need to be able to do in calculus. And I will say this really is just going to be an introduction to differential equations. Way back when I was in college and actually majoring in math, I had a whole semester, actually had 2 semesters of just differential equations. So this is just the introduction to a whole other world of math. Things that we're going to be focusing on this unit is what is a differential equation, how we analyze it, how we can approximate functions using differential equations, and then also there is 2 types of word problems that we'll look at. The word problems we really won't get to until after the quiz with proportionality and then logistic growth. Also, that being said, kind of talking about this unit, did finish grading your test yesterday. Those grades should be in Infinite Campus. I did post the answer key in the answer key folder. Definitely look over your test. Most people did fairly well on it, but do kind of look at your mistakes just to get all that topic down. So looking at differential equations, let's kind of start off by just reviewing what a differential equation is. In math, a differential equation is actually a very, very broad kind of term. And for us, a differential equation is basically just going to be defined as an equation, meaning that there has to be an equal sign in it with derivatives. Which is a very, very broad kind of definition. There are going to be lots of different types of differential equations. I kind of have just scattered at the bottom of this page different types of differential equations that we have. So if I just say y prime is equal to 5x plus 6, technically that's a differential equation. But we can also look at ones that are a little bit more complicated. So we could have derivatives in terms of y, like y prime is equal to 6y. That's a differential equation. We could also have ones that mix together x's and y's, like y prime is equal to x squared plus y squared. And we can also have ones that use the second derivative or a combination of the first and the second derivative. In all of those, just because it was easier to type up using that font, I use y prime and y double prime. I will say for the sake of a lot of the math that we do with differential equations, we tend to use the dy dx notation instead of the prime notation, just because it makes certain things a little bit easier to solve and set up. Today's notes, we're going to focus on kind of 2 things. The first thing we're going to focus on is slope fields. So that's going to be kind of a new thing. And then the second thing that we're going to focus on is just interpreting differential equations. This unit, I hope by the name of it, differential equations, it has a lot of derivatives in it. So all that stuff we did first semester is going to be kind of showing back up a lot. So intervals of increasing and decreasing, absolute extrema, relative extrema, tangent lines, implicit differentiation, related rates, I don't know. All that stuff we do with derivatives shows up in kind of this unit. So it's kind of a good unit to review with of that old material, but it will show up in this problem as well. So the first thing that we're going to look at is something called a slope field. And a slope field is basically going to be a representation of the derivative. And there's going to be 2 types of slope fields you're going to be expected to be able to interpret and use on the AP exam. The first one is you should be able to know how to create a slope field, which is what we're going to look at first. The second thing that we're going to look at, which is probably more of an applicable tool in 2021, is how can you reinterpret a computer-generated slope field? Because normally they're going to be computer-generated, and you just have to be able to interpret it. We're going to start by just creating the slope fields first, not that one. And so what is a slope field? Think of a slope field as a representation of the function of all the possible plus c's. So what I mean by that, we have dy dx is equal to 2x. We know that dy dx is just like y prime, that is the derivative. So we have this function, its derivative is 2x. You can probably kind of think about what that function was originally, but we're just going to think of it as the derivative now. dy dx is equal to 2x, and we are literally going to plot on a coordinate plane at indicated values. Little like baby slopes, if you will, to kind of represent what the slope is at each point. So we're going to use kind of like a modified t-chart. So like I already did some of the more tedious work of each of those points. I went ahead and just listed the coordinates here. And we're just going to plug that coordinate into dy dx. Some differential equations will just be in terms of x. Like this one is 2x. It's just in terms of x. Sometimes they might just be in terms of y. Sometimes they might be relying on both the x and the y coordinate. This one is just in terms of x. So like plugging things in, like 2 times -1 is -2. 2 times -1, -2, basically all those that have an x coordinate of -1 has a slope of -2. So that's like the math part of it. How do you represent that? So what this basically means is at the coordinate of -1, 0, this function, whatever the original function was, has a slope of -2. So I'm going to go to that point, -1, 0, and just draw a little baby slope that's approximately -2. Same thing at -1, 1, also -2, and -1, 2 also has a slope of -2. We're going to do that for each point. It is tedious, but at the same time, you like it when this shows up on the AP exam because it's pretty easy to do. When x is 0, 2 times 0 is 0. So I know that we have horizontal tangent lines pretty much on the y-axis. And then I can just kind of keep repeating that. 2 times 1 is 2. Whenever x is 1, there is a slope of 2. And then when x is 2, 2 times 2 is 4. So I'm going to draw one a little bit steeper to represent the slopes of 4. How will the AP exam grade this? So they're not asking you to make your tick marks exactly a slope of -2. How this is graded on the AP exam is any slope that should be horizontal should be clearly horizontal. Any slope that should be vertical should be clearly vertical. Any slopes that are positive should be increasing. Any slopes that are negative should be decreasing. And any slopes that are the same should appear parallel. So like you're not doing like a perfect sketch, but roughly you want to kind of see what that graph looks like. And that would be the answer. That is the slope field. You can kind of see where it gets named. It's literally like a field of slopes. Now what this represents is we know that this is a derivative. When we integrate functions, what do we always have to include at the end of our antiderivative? Plus c. So you can kind of imagine if you were to kind of like draw a function in the slope field, you can kind of almost visualize all these different plus c's in the problem. Next slide, this is my computer generated one, just so you can kind of see more exactly what the slopes look like. So again, dy dx is equal to 2x. There is the slope field of that problem. Underneath that, I have some interpreting that I want to do. So we already sketched the slope field, but I have on the axes provided, sketch the graph of the particular solution, y is equal to f of x, to the equation using the initial condition f of 0 is equal to 1. Well, what the heck is that saying? That's telling us that we have this function. It has the initial condition where f of 0 is equal to 1. So I know that at 0, the function is equal to 1. I know that point is on the graph. It's asking you to use the slope field to draw in basically the original function that has that as its derivative. And it's kind of like connecting the dots, but it's kind of like just connecting the slopes instead. If I want to draw the function that goes through that point, so at this point, it has a horizontal tangent. Moving toward the left, kind of following the slopes, goes up. Moving to the right, again, just following the slopes. I see that it does make kind of this parabola shape. I think it makes sense that it's a parabola, so I have kind of on this question underneath it. It says find the general solution. Well, this is the derivative, dy dx is equal to 2x. If I want to find the original function, I just want to integrate the derivative. Well, what's the integral of 2x going to give you? X squared plus c. And you can kind of look at the graph. Well, yes, that does look like an x squared plus c. You can kind of imagine for different c's, it could be located further up or further down. And then also review, again, there's going to be a lot of questions that will be reviewed from previous units. Find a particular solution. That's just telling you to find the exact equation that goes through that point. So when y is 1, x is 0. This one works out easily because I made it easy. C would be equal to 1. So the particular solution will be y is equal to x squared plus 1. Which, if we go back to look at the slope field that we drew, that particular solution that we had is the equation x squared plus 1. Now this one was an easy one because we could integrate this function by hand. Why slope fields are going to be important to us is we're going to start seeing some derivatives that we can't integrate by hand. So we're going to have to rely on the slope field to kind of help us interpret the graph and kind of imagine what that graph looked like. Go ahead and try the second one for me. It's example 2a. Again, there is an answer key kind of on the next slide, but go ahead and just kind of quickly for me create a slope field for this function. Do make sure you look at this one. This one is dy dx is equal to 2y. So this one has a derivative that's basically in terms of y. So basically still plug in the coordinate. This one you're really just going to be plugging in the y coordinates. And then just kind of like estimate some slopes and draw it out. And then we're just going to kind of analyze it as well. We'll use the slope field to kind of figure out like what could the original function possibly look like. And then talk about some other things relating to this derivative. But take a moment to try that one for me. Again, it's tedious, but kind of filling the t-chart. Anytime y is 0, 2 times 0 is also 0. Anytime y is 1, 2 times 1 is 2. And then anytime y is 2, 2 times 2 is 4. Again, your slopes don't have to be perfect, but ones that are horizontal should be clearly horizontal. Positive ones should be increasing, and ones that are the same should look parallel. I'm going to go ahead and cheat and just look at the next slide. But that is basically what your slope field should look something like. Now this is one that we don't know how to integrate quite yet. We will actually learn eventually how to integrate it when it's in terms of y like this. But if you were to make a guess, looking at this slope field, what do you think the original function that has a derivative of 2y would be? What type of function? If you're looking at those slopes. It looks like an exponential one. I hope it looks like an exponential one to you. You kind of see like the horizontal asymptote and kind of increasing. We can kind of verify it, so similar to what we did to that previous one. I have on the axis provided, let's sketch a graph of the particular solution. So that's going to be graphing the original equation that has the initial condition of f of 0 is equal to 1. So like I know this graph is crossing at f of 0 is equal to 1. And then just let all those little slopes kind of be your guide. So like at 0, 1, it's definitely increasing pretty steep. Moving to the left, again, we're not really going to cross a slope. You can kind of see how it levels out. Moving towards the right, you can kind of see how it just keeps getting steeper and steeper. So we can visually see, even though we don't have the skills yet on how to integrate this one, we can kind of interpret it and see like, oh, this is the derivative of an exponential function. Since we can't integrate this one yet, the other skill that I want to kind of look at is how we verify that something is a solution to the differential equation. And that's what we have, I typed in at the bottom. So I say that verify that y equals e to the 2x is a solution to the differential equation. And I'm just going to rewrite it down here. dy dx is equal to 2y. This unit is going to love a verify or show type question. Whenever you see a verify or show, like it's giving you like the starting point and the ending point, and you just have to provide all the algebraic steps in between. On the AP exam, a question like this, your work would be what is being graded, so you would just want to make sure that your steps are very clear and obvious. So basically what this question is telling you is, hey, y equals to e to the 2x is a possible function that has a derivative of 2y. Show that that function does have a derivative of 2y. Any ideas of what you could do to show that that function does have a derivative of 2 times y? Take the derivative. Like we're talking about derivatives, let's find it. So we have y prime, and again, I'm going to use dy dx more instead of y prime in this unit, just because that's how we often will write differential equations. Derivative of e to the 2x, making sure we use the chain rule, that's going to give us e to the 2x times 2. Again, we're looking at kind of the end, this is the goal. I have e to the 2x times 2, I want this to look like 2y. Anyone see how we can make that look like 2y? What do we know e to the 2x is equal to?
You plug in y for 2x.
It's just y, don't overthink it. That is the y. So how do we clearly show that? Like I'm just going to show my substitution, that becomes y times 2, which is of course the same thing as 2y. And I have shown now that the derivative of e to the 2x, yes, that is e to the 2x times 2, but that's also the same thing as 2 times y. So we can verify it by kind of connecting the dots. Try this third one for me. Create a slope field pretty quickly. This is one that we actually will never solve by hand. We do not learn the methods in AP Calculus on how to solve this one by hand and figure out what the original function is. But we can still analyze it using its slope field. This one is kind of unique because each point slope is being affected by both the x-coordinate and the y-coordinate. So like if I'm trying to find the slope at -1, 0, we have 2 times -1 minus 0, or -2. A little bit more tedious to find, but go ahead and try that one. I will say on all the AP exams that I've seen, the most number of slopes they make you draw is usually 9. So this one has, what, 12? But usually the most they make you draw is 9. So go ahead and try this one, and then we'll look at this one, which is a little bit harder to kind of verify because it isn't as direct. So go ahead and try that slope field for me. And of course, once you finish, when I check it, like it's going to be on the next slide, just so you can see a computer generated one. But again, hopefully if you're ever asked to create a slope field, you kind of smile because you know that should be some guaranteed easy points, because it's literally just a fancy T-chart and drawing little baby slopes. And so that is what you should be getting. I know some of you might still be working because it is kind of a tedious thing about drawing some slope fields. Again, things how you want to interpret this, like when we see a slope of 0, that's like, hey, the original function has a horizontal tangent there. And again, what the slope field represents is kind of like all the possible original functions. So like all the different values of c that you could have. Of course, you're not plotting it at every single point. But it does give you an idea of what the function looks like. So similar to what we did on all the other ones, let's draw the function that goes through f of 0 is equal to 1. So I have f of 0 is equal to 1. I know this point is on the graph. If I want to trace out what this function looks like, how would you describe what this function possibly looks like? It's a parabola. It's not actually an exact parabola, but it's like parabola adjacent. But we can kind of see moving towards the left. Again, just kind of let the slopes be your guide. Moving to the right, you can kind of let the slopes again be your guide. So it does have like this parabolic-ish shape. I know it's not a parabola just because I know where it's going to come from, but it does have that shape as long as you're just kind of following the slope field. So similar, this is one that we do not know how to solve, but let's kind of verify a solution. So I have verified that y is equal to 3e to the negative x plus 2x minus 2 is a solution to that differential equation. And again, that differential equation was 2x minus y. And so again, what that is basically asking us to do is it's telling us to verify. So we want to provide all of the steps kind of in between. We want to show that that function has a derivative of 2x minus y. What might be the first thing you try to do if you're trying to show that that is the derivative? Just take the derivative, all right? So we have y, its derivative is y prime or dy dx. So that's going to be 3e to the negative x times negative 1 from the chain rule. The derivative of 2x is 2, and of course the negative 2 goes to 0. We want to show that this dy dx is the same as the other dy dx. Two routes you can kind of take. For this one, there's like a long way to do it and kind of a shorter way. For me, a shorter way is sometimes like if you can't work a problem easily all the way down, like find a way to meet in the middle. So like we want to show that this dy dx is the same as the original dy dx. Well, if I'm looking at the one that I have in red, ways I can do that is, well, dy dx is equal to 2x minus y. Well, what is y equal to? 3e to the negative x plus 2x minus 2. Distributing, so I have 2x minus 3e to the negative x minus 2x plus 2. Don't want to ever skip steps for a problem like this because, again, your work is basically the justification. The two x's cancel out, and we have negative 3e to the negative x plus 2. So we have shown that, yes, those derivatives are identical.
Mr. Brown.
One way to do this, and I'll take questions. Again, not everyone does it this way, but people will see this dy dx and say like, hey, that looks kind of close to that y up there. And you could do some weird substitution where if I subtracted that 2x, yeah. And then end up doing, hold on, minus, try it again. And then do like some weird substitution after factoring out a negative from the one I have in purple. I think that's the longer way to do it and not that obvious, which is why I kind of suggest just meeting in the middle for these problems when you have to verify. Someone started to ask a question, I interrupted, so go ahead.
I was just gonna follow that second track, and what I did was I just subtracted the y, then subtracted the 3e to the negative x, and added the 2, and that was it. Just
so yeah, that would work too, and that would keep you from having to factor out the negative to do the substitution.
I was just wondering if that was okay.
Yeah, it will be allowed as long as you're doing correct algebra and you either meet in the middle or show that one of the dy dx's is the same as the other, like you have verified it mathematically. Any other questions on slope fields part 1? All right, let's look at slope fields part 2 then. What time is it? We're good. So one thing we often do when we're looking at these problems is approximations. And approximations, like I don't want to get into too much details about it, but like we will be approximating a whole lot the next 2 units of like different ways we can approximate with functions. We have 3 types of approximations in calculus. We have tangent line approximations, which we're going to look at today. We have Euler's method, which is what we're going to look at tomorrow. And then we have Taylor series and Taylor polynomials, which is all of next unit. And those are all just types of approximations. The easiest one by far is going to be a tangent line approximation. So let me kind of set up this problem for you. We have this differential equation dy dx is equal to x minus y. I provided to you in OneNote kind of a computer-generated slope field of that one. That's a whole lot of points and decimal, so that's what the slope field of that differential equation looks like. And I also have the initial condition f of 0 is equal to 2. I know you don't know this now, but this is a differential equation that we cannot ever easily integrate with normal methods in calculus. Like, we just can't go back and find what the original function is. But we still want to be able to talk about the original function. Like, maybe it's representing some word problem, we need to find a certain y value of that function. So since we can't find the function originally, we would kind of just want to be able to find different ways to approximate it. One approximation that's not really like a very calculus one, because it's kind of just like you're drawing, is just like, hey, draw in the equation, and then just use your drawing graph to kind of estimate what the value would be. So I'm saying that f of 0 is 2. So f of 0 is 2. So I know this is on the graph. And this first question says, hey, sketch a graph of it, and then use that sketch of the graph to approximate f of 1. So again, I'm starting at f of 0 is 2, and I'm going to kind of follow the slope fields. And again, just kind of let the slopes be my guide. And so my function, whatever it is, looks something like that. Is that perfect? No, but we're just kind of using the slope field to guide us to the correct answer. So then I can kind of estimate it. Like, I don't know what f of 1 looks like exactly, but I can estimate it by using that curve that I drew in. Using that curve that you've drawn in, what would you say f of 1 is approximately? 1.25. Again, do we know that is exactly f of 1? No, because we don't know what that function or curve is. But we can kind of use the slope field as our guide. Now, we often want one that's a little bit more mathematical. Like, we don't want to have to just rely on like how we drew it. That's not always going to be exact. That's not always going to be useful to us. And so another way to find approximations is a tangent line approximation, which you actually might recognize from some of that first FTC homework. I snuck one of those in there before you technically knew what it was. And a tangent line approximation, the reason why it works is that if you think about it, if you have some curve and a line tangent to that curve, as long as you're staying pretty close to that point of tangency, the tangent line and the curve are basically the same. They're not exactly the same, but they're close enough, and we can kind of use that close enough to like approximate values. So whenever you're asked to find a tangent line approximation, you basically find the tangent line and then plug the value you're approximating into your tangent line. So let's kind of review tangent lines. We know tangent lines, the basic format, y minus y1 is equal to the slope times x minus x1. We know the initial condition is at 0, 2. So I'm going to have y minus 2, still need the slope, x minus 0. Well, to find the slope, what do we use in calculus to find the slope? The derivative. Well, what is the derivative for this problem? It is dy dx. What was dy dx? X minus y. So what's the slope at that point? Dy dx, x is 0, y is 2. The slope is negative 2. So that would be my slope. That is my tangent line. Kind of simplifying it, we get y is equal to negative 2x plus 2. So that's my tangent line. And again, the idea behind this one and why it works, I'm going to kind of draw it in for us, is this tangent line close to the point of tangency. The graph is fairly close to that tangent line. So this one is zoomed in pretty far because of the scale, but you can imagine that this tangent line is close to the curve. So I'm just going to pretend that the tangent line and the curve are practically the same. So if I wanted to estimate f of 1 is approximately the tangent line value at 1. Well, 2 times negative 1 is negative 2, plus 2 is 0. So from that tangent line approximation, we're going to say that f of 1 is approximately 0. And you might be looking at this and like, Mr. Brown, I'm pretty sure we had a more accurate estimation by drawing the curve. Probably yes in this case, but most of the times you're not going to have a slope field in front of you, / you don't want to have to spend all that time making a slope field. So that's why a tangent line is going to be the better option. It is also more like algebraic, and believe it or not, tangent lines will actually be expanded eventually into like Taylor polynomials and all that we'll do next unit. Similar to whenever we do approximations. So when we did Riemann sums, we wanted to know whether that area was over or underestimating the actual area of the graph. We want to know whether that tangent line is over or underestimating the actual value of the graph. Looking at this one, so we use this value down here to estimate that value up there. So clearly our estimate is an underestimate. What makes the tangent line in this case an underestimate of that curve? Or in other words, what's forcing that tangent line to be below the curve? It's concave up. So we're going to talk about the concavity of it. So again, one thing you just want to kind of know, and again, it's pretty easy to figure out if you just draw a quick graph. A tangent line approximation is going to give an underestimate if the curve is concave up, because the tangent line will end up under the curve. So it will give an underestimate if the curve is concave up. And I just put down there, but concave up. Likewise, if your curve is concave down, the tangent line ends up above it, so the tangent line would give an overestimate. And we'll spend more time with approximations, but I did just want to kind of get started with that for today. And then I have 2 more slides, and then we'll be done. So, last 2 slides. Do you want to start off by saying, again, anything we have ever done with the derivative can show up in differential equations. There's no way for me to go over every single type of problem that you can ever encounter, because honestly, we did all those types of problems first semester, now we're just kind of throwing in differential equations into them. So here's one. I based this one off of an AP question. I did provide the slope field for you. Again, it's that same slope field from the previous slide. If this was on the AP exam, there wouldn't be a slope field to kind of look at. So I kind of just include that there to help us answer the question and to kind of see why the answer is true. But we're going to rely on our calculus to mainly answer this question. So it says, consider the differential equation dy dx is equal to x minus y. And we want to describe all the points at which solution curves, so that's going to be like the original function, would be increasing. Well, from first semester, what would it mean if the curve was increasing? The derivative is greater than 0. So if it's increasing, we know the derivative has to be positive or greater than 0. Well, what is the derivative? dy dx, they gave it to us. So really, what are we going to try to show? We want to find all the places where the derivative is greater than 0. That's what increasing would mean. What is the derivative? The derivative is x minus y, which is greater than 0. That's not really a good description. Like, that doesn't really give you any idea what that looks like on the graph. Like, hey, whenever you subtract the y coordinate from the x coordinate, you get 0, and your r is bigger than 0, then that means it's increasing. Normally, for a problem like this, you're going to want to solve it for y to kind of get it in the form of like a line or something. So like adding y to the other side gives you x is greater than y. Flipping that around, that's the same thing as saying y is less than x. So if I want to describe all the points at which solution curves would be increasing, using this inequality, let's kind of think about what this inequality means. This would be all the points below the line y is equal to x. So again, what are we even meaning by when we say that? It means that anytime you try to draw in the function, As long as those points are below the diagonal y is equal to x, we should have an increasing function. Now, normally the slope field will not be provided. I copied it over just so you can kind of see that our answer really is and honestly true. What is y is equal to x? It's this diagonal. I'm using a dotted line because it's y is less than x. If you wanted to shade this one, when y is less than x, it will be everything below. And when you're looking at this graph, what do you notice about all the slopes less than that dotted line? They're all increasing. So we would know, like, if you were to draw in a function, it doesn't have an initial condition, but any function you kind of draw in, like, they all would be increasing. Sometimes these questions are worded differently, like it might say, like, hey, in which quadrants would the function be increasing? Or what would x need to be for this graph to be decreasing? So you can kind of just use the function to kind of figure out, hey, when is the derivative positive or when is the derivative negative? Part 2 of the question, this is where we're going to stop at for today. Let's talk about concavity. We did that first semester. So I have that same differential equation, and we want to describe all the points at which the solution curve will be concave up. So where on the coordinate plane would all the solutions of this differential equation be concave up? So let's remind ourselves about concavity. What does it mean mathematically for it to be concave up? The second derivative is positive. Like we know that from first semester. This is the first derivative, but basically we want to show when the second derivative is greater than 0. Like that's what we want to find and kind of show. Well, this is dy dx. How do I find the second derivative? Not your question. Take the derivative of it. So this is dy dx. We have the second derivative of it. Do you want to emphasize that this is the second derivative with respect to x? So let's go ahead and take the derivative. What's the derivative of x with respect to x? 1. And then I have minus, what's the derivative of y with respect to x? dy dx. So your friend implicit differentiation just showed back up. The long way to think about it is, what's the derivative of y? It is a 1, but we had a y. I really wish it was an x. So implicit differentiation, you thought you were done with it. Definitely came back to find you. That's not a really useful version of the second derivative because it's in terms of dy dx. A better version of the second derivative would be 1 minus, well, what is dy dx? X minus 1. So kind of simplifying that, your second derivative is 1 minus x plus y. Let's not forget what we're trying to show. If it's concave up, what do I want this value to end up being? Greater than 0. That means a whole lot of nothing. It's a lot easier to do if you like solved it for y. So like solving for y is greater than x minus 1. So if you wanted to describe all the points that were concave up, how would you verbally describe all the points that are concave up?
All the points that are above the line.
Everything above that line. So basically all points above y is equal to x minus 1. Again, on the AT exam, you wouldn't have a slope field to kind of justify your answer. I like how you can kind of see how the answer is true. So what is x minus 1? It's going to be this dotted line. All the points above it, you can kind of see. If you're to draw in just any function, you could kind of fall in the slope fields. What do you notice about all the curves above that line? They are concave up. So we can kind of see that our answer is true. All the points above y equals x minus 1 ends up being concave up. So again, there's tons of different problems I can ask you to kind of analyze differential equations. I possibly can't go over all of them. It does use a lot of stuff that we saw first semester. So what I want you working on first, there's kind of like your checklist, to-do list. Go ahead and do homework 1. It's differential equations and slope fields. Some of it's pretty easy. Some of it you might have to think about a little bit. The first page is pretty skill-based. The second page has questions based off of old FRQ questions. Other just announcements, like clearly go back and look over your old test. If you need to do recovery, then definitely reach out and we'll figure out a time for you to do that. Also, if your briefcase binder grade wasn't a 100, I'll still take parts of that you end up completing as well. And yeah, that's about all I have to say about that. So I can go ahead and get started on homework 1. Tomorrow we're going to expand on these problems and talk about something called Euler's method, which is a BC only topic. It's actually a pretty easy BC only topic, which is nice. As long as you can like add and multiply, you're going to be good. But it's going to be another way to do a little bit more of a better approximation than tangent lines. So yeah, we'll do Euler's method tomorrow, weekend, and then after the weekend will be separable differential equations, where we actually start solving them. So if you're at home, you're welcome to leave and get ready for your next class.